Okay, hello and welcome to Chapter 6.3, Kinetic Energy and the Work Energy Principle. So far we've talked a little bit about work and how it is a form of energy. Now we will be talking about energy in more depth. So first we will be discussing energy can be represented in many different forms. For example, electrical energy or energy in terms of heat. But in this chapter, we will be talking about translational kinetic energy, meaning energy of motion. Okay, so let's write this down. We are talking about kinetic energy. Energy of motion. It comes from the Greek word kinetikos, meaning motion, the word kinetic. Okay, let's, for example, take a car that is moving along on a flat road. And in this situation, we are going to have a constant acceleration. This will be our v1, and here we will have some v2. So constant acceleration, our net force here will be constant. And we will have some net displacement, d. Okay. If you recall, we have our formula of motion, v squared equals v1 squared plus 2ad, which we can rewrite as a equals v squared, v2 squared minus the initial velocity squared over 2d. Okay, so this describes our constant acceleration. And we know that work, sorry, writing outside there, work, our net work will equal F net times d, which we know we can write as mass times its acceleration times that displacement. And now we're going to replace A with this form here. So we're going to get this formula inside. And notice our D's are going to cancel out here, and we are going to be left with a simpler formula for work. Okay, so we have this formula for the net work. 1/2 the final velocity squared minus 1/2 mv1 squared, the initial velocity squared. Okay, we can define these quantities, 1/2 mv squared, to be the translational kinetic energy. Okay, so we're going to write that as Ke for kinetic energy, and it equals 1/2 mv squared. Okay, so this is an important equation to remember. This is our kinetic energy. Now we say translational kinetic energy to differentiate it from rotational kinetic energy, which would have a different equation in terms of the energy associated with rotational motion. So how do we relate this to this? So we have kinetic energy terms here. Well, the work is actually the change in this kinetic energy. So we see that work, now let's see, yeah, we can write it as the net work here equals Ke1 minus, sorry, Ke2 minus Ke1. So it equals the change in kinetic energy. So this is the work energy principle, and it is an important relationship. We will find many uses for this in our future lessons. So the net work done on an object is equal to the change in the object's kinetic energy. So this is a useful topic, a useful formula for us to use in situations in which we would not have been able to solve with our previous knowledge. For example, this question. So a car is a bit of a complex situation. There's tires moving and there's friction and all kinds of things going on. But we can use this simple formula here to simplify the situation. We consider a car to be a simple system, basically a simple particle moving through space. And so we can use our formula here to help simplify that situation. So first we start by saying, well, work is going to equal the final kinetic energy minus the initial kinetic energy. Okay, so the final answer is 2.5 times 10 to the 5 joules. A lot of energy there. I want you to realize that you would not have been able to find this answer with the knowledge that you had before. You had to know something about the force in order to solve this question. But here, just with information about velocities, that's enough for us to find out this important value of the energy associated with this acceleration. We have a car and we want to stop it. So suppose we have a car traveling at 60 kilometers per hour. This car can brake in a distance of 20 meters. So when d is 20 meters, this car is going to brake. If the car is going twice as fast at 120 kilometers per hour, then what is the stopping distance? Okay, so it can stop after 20 meters if it's going at this speed. If it's going at 120 kilometers per hour, how quickly can it stop? Okay, we're going to assume the maximum braking force is approximately independent of speed. Okay, so it doesn't matter how fast you're going, the force of braking will be the same. Okay, so we're going to again assume that the car is a simple object that's moving through space, and the net stopping force F is approximately constant. Okay, so we know that the net work done on the car is FD cosine of 180 degrees here. Okay, why is it 180 degrees? Well, if you think about the car traveling here, as it's traveling around on the road, its motion is like this, but the force is in the opposite direction. This is the braking force. Yeah, so actually the direction of motion, if it stops over here, this would be our displacement. The direction of displacement is opposite the direction of force. So we have 180 degrees, and we can write minus FD here. Okay, so I'm going to erase this drawing. Now, well, that's the net work, so let's write that over here. And now we use our kinetic energy theorem. Okay, we're relating the net work to the change in kinetic energy as we had done before. So 1/2 m, and now I'm just going to group these here together for simplicity. Okay, the initial speed we know is going to be 120 kilometers per hour, but the final velocity is 0. Okay, so we have 0 and then minus our 120 kilometers per hour. Now we're not in SI units here, but you will see that it's not necessary because what we have here, I'm going to bring out the minus sign, is 120 is 2 times 60 kilometers per hour squared. So this is what we had before, okay? And now we are squaring this, okay? So I can bring out a 4. So this is 4 times what we had before, actually. So the stopping distance is going to be 4 times the original value. So what we find is that our new D value is going to be 4 times what it had been earlier, so 4 times the 20 meters. Okay, so the answer would be 80 meters. What this means is that the displacement is proportional to the velocity squared. Increase the velocity a certain amount, the displacement associated with that velocity will be the velocity squared.